Here, this distance is the square root of x squared plus y squared. So how can we express that in terms of rho and phi? That would be this distance right here as well. Rho sine phi. All right, so now to get x and y individually, we incorporate theta. So x is going to be rho sine phi cosine theta, and then y is going to be rho sine phi sine theta. So that's how you convert from spherical coordinates to Cartesian. Suppose we have a point x, y, z, 1, square root of 3, minus 4. So how do you convert to get rho, phi, and theta? Well, the first thing you do, you get rho most easily. So that's the square root of x squared plus y squared plus z squared. So we get 1 plus 3 plus 16, square root of 20, so it's 2 square root of 5. So once you have rho, what's the easiest thing to get next? And how do you get it? Because we still need to get theta and phi. You can use x and y to get theta. You can get z to get phi. So I guess kind of a toss-up as to which is the easiest one. So we'll go ahead and get phi. So phi is inverse cosine of z over rho. And the nice thing is, there are no gimmicks to worry about, like with polar coordinates, because polar coordinates you have to correct the angle, but phi is between 0 and pi. Inverse cosine is also between 0 and pi. That's the range of it. So you can just accept what your calculator gives you. In this case, you get roughly 2.678 radians. And then we get theta in a way suggested. Y over x causes a rho and a sine phi to cancel out. So we get tangent theta. So it's the exact same relationship as in polar coordinates. So now we can get theta without too much trouble. Alright, so tangent of theta is y over x, which is the square root of 3. So in this case, x and y are both positive. There's no problem. We know exactly where it is. It's in the first quadrant. So theta is going to be pi over 3. So those are the spherical coordinates. Rho, theta, and phi is 2 root 5, pi over 3, 2.678 radians. So compute your rho, square root of x squared plus y squared plus z squared. Use x and y, just like in polar coordinates, to get your theta. Use inverse cosine with z to get your phi.
When to use polar, cylindrical, or spherical coordinates?
For a particular integral?
Yeah.
There are certain things you can look for. For instance, if you see expressions involving, say, x squared plus y squared, that's a suggestion to use cylindrical if it's a triple integral, or polar if it's a double integral.
Okay.
If you see, for instance, x squared plus y squared plus z squared involved somehow, either in description of a region or the integrand, that's a suggestion to use spherical coordinates. So there are certain clues in the problem. To look for those things,
okay,
that's a safe bet. Because then you can condense those expressions down to a single variable, like r or rho. Now, with polar and cylindrical, you have to put an extra factor of r in the integral. There's an extra factor of spherical as well. You have to include a factor of rho squared sine phi. So when you convert an integral to spherical coordinates, you have to remember to put that in. So you're integrating over region H. The integrand is x squared plus y squared dv. And the region H is above the xy plane. So it's above a plane z equals 0, and it's below the sphere, the unit sphere, center to the origin, radius of 1. So basically we're just looking at a hemisphere, upper half of this sphere, radius 1. So what we need to know is, what are the limits in terms of rho, theta, and phi? Rho first. What would rho extend from? So you want to cover the whole inside of this. And rho is distance from the origin in this case. Yeah, it's going to extend from 0 to 1, so each one of you got one of the limits. So those are your limits in rho. All right. What about theta? So theta is the angle that x and y make. It's nothing to do with z. And so here we've cut this off at z equals 0, here's the z-axis right here.
If it's the angle that x and y make, would it just be from 0 to 2 pi since
Yes,
it's a circle?
you would cover the whole thing. Yeah, you sweep all the way around. So theta goes from 0 to 2 pi. All right. Now, what about phi? Remember, phi, certain values of phi correspond to North Pole, equator, South Pole.
Be 0 to pi.
Not quite. Yes, 0 to pi over 2. Pi over 2 is the equator, pi is the South Pole.
But are we not considering the other half of the circle?
So down.
Oh,
So
okay.
yeah, we're
That
going.
makes sense.
Yeah.
Gotcha.
0 to pi over 2. All right. So now we have the limits are nice and simple. They're just constants. Now, as far as writing the integral, all right. So we'll have 0 to 1 for rho, 0 to 2 pi for theta, 0 to pi over 2 for phi. So at least some room here for the integrand. We just got to figure that out. And then we're all out of here. D phi, d theta, d rho. Okay. First we need our extra factor, rho squared sine phi. So let's just put that in there right off the bat. But then we have the integrand, which in x and y terms is x squared plus y squared. But we need to express that in spherical coordinates, which unfortunately I just erased. So I'll put them back. All right, so we need to express x squared plus y squared in terms of these spherical coordinates. So because of cosine squared plus sine squared equal 1, theta drops out. So what we get is rho squared sine squared phi. So our actual integral is rho to the 4th sine cubed phi d theta d rho. Yeah, it worked out quite nicely. Much nicer if it would have none of these stayed x, y, z. All right, rho to the 4th, we can just put that out here. That's no problem. Here we have an integral with respect to phi that we got to figure out right away. How do you do that? We actually saw something like that recently. When it's an odd power of sine or cosine. What?
Split it up.
Yeah, you split it up. So you write this as sine squared phi sine phi, which is 1 minus cosine squared phi sine phi. So you have sine phi minus cosine squared phi sine phi. This you just do directly. This, you let u be equal to cosine. And then du is going to be minus sine phi d phi, which will absorb that. So you're integrating, you end up integrating u squared. So that ends up working out too. A lot nicer than a trigonometric substitution. So once you work that out, this only depends on phi. You'll get a constant, which will be multiplied by 2 pi. It'll be back out here with a simple integral of rho to the 4th d rho.